Welcome. My name is Madeline Bolden, and I will be teaching you today. And as we go through our class, I would like for you to think about our guiding question. What is the definition of a tangent line to a curve? As we ponder the guiding question, we need to think about what a tangent is. And I'm sure that you've learned about a tangent as it relates to a circle. And we know that a tangent to a circle is a line that intersects that circle at one point. The tangent line must be at a 90-degree angle or right angle to the radius that intersects the line at that same point. However, when we apply this definition to other kinds of curves, like the one you see here, it falls apart. And we need to develop a definition that will work not only for the circle, but also for other kinds of curves. We will discover this definition through finding the equation of the tangent line t to the parabola y equals x squared. Let's focus on point P at 1, 1. We want to find the equation of the line that goes through point P at 1, 1. We want to do this because we will be able to show that the coordinate pair 1, 1 is shared by both the curve y equals x squared and the line t. This proves that the line t actually touches the curve at exactly one point, P at 1, 1, making it a tangent line. We know from our algebra classes that in order to find the equation of a line, we need two items, a point and the slope of the line whose equation we are trying to find. I want to share with you that we could find other lines from other points on the curve y equals x squared and find the equation of those lines. The equation of those lines would be different from the equation of the line at point P at 1, 1, but they would be equally as valid because those lines would also be tangent lines on the curve y equals x squared. However, we will focus on finding the equation of the line passing through point P at 1, 1. We have been given our point 1, 1 on line T, but we do not have a slope. We know from our algebra courses we need 2 points from the line to substitute into our slope formula. Slope is abbreviated m, and the formula is as follows. It is the change in the y values divided by the change in the x values. So we have a dilemma. How will we find the slope of line t? We will look to Isaac Newton for the answer. He found that we need to draw a second line called a secant line going through point P at 1, 1 and a second arbitrary point on the curve Px at x squared. Now let's focus on our secant line, the blue line, intersecting our curve y equals x squared at 2 points. We can easily find the slope of the secant line by substituting our point P and Q's coordinates into the general slope formula shown here to attain the slope of the secant line shown here. Now, here is the important discovery Isaac Newton made, which is the foundation of calculus. If we move point Q closer and closer to point P by moving down the parabola, our secant line, the blue line, will fan outward. The closer and closer Q gets to point P, the closer the blue line would look as though it is superimposed on top of the green line. We can draw a valid conclusion of what the slope of the tangent line would be by recording the series of slopes of the secant line as we move point Q infinitely close or as close as we can to point P. A numerical analysis is a table listing numerical values to analyze in order to draw valid conclusions about the behavior of functions. Our specific numerical analysis here shows randomly selected x-coordinate values for our point Q. Our values begin at x equals 2 and moves down to x equals 1 and 1/10,000th, a x-coordinate very close to x equals 1 of our point P. You may be asking yourself, why were the x-coordinates only listed and not their corresponding y-coordinates? Because we only need the x-coordinates to substitute into our slope formula to obtain our numerical values for the secant line. As we substitute each x-coordinate into our slope formula, we get a corresponding numerical slope that we can analyze. What pattern do you see here in this table? I hope you are able to see that as our x-coordinates approach x equals 1, the slopes of our secant lines approach 2. I think it is fair to say that if we extend our numerical analysis to include x-coordinates even closer to x equals 1, then I have here, the slopes of our secant lines would get even closer to 2. But before we close the book on finding the slope, let's consider one more possibility. Mathematicians must consider all possibilities when drawing a conclusion about a particular phenomenon. In our problem, we must consider the fact that we can approach P at 1, 1 from a different direction. In our original graph and numerical analysis, we took x-coordinates that were greater than 1 and moved down our parabola toward P at 1, 1. Now we must consider x-coordinates less than our point P. We shall name our new point R. I realize I have point R situated at the origin here, but I'm still going to generally name R's coordinates x and x squared because point R can be any point less than P. We create the numerical analysis again of randomly selected x-coordinates starting at x equals 0 and move up the parabola to x equals 9,999/10,000ths. As we substitute our x-coordinates into the slope formula, what pattern do you see emerge? I hope you can see that as we move point R up the parabola 2.11, our corresponding slope values approach 2. As we look at our numerical analyses side by side, we can clearly see that as x approaches 1, either from a greater point, x equaling 2 going to 1 and 1/10,000th, or from a lesser point, x equaling 0 and going to 9,999/10,000ths, we see that our slope values are approaching 2. So it leaves us no doubt that the slope of our line T is 2. We use the point slope formula to find the equation of the tangent line. Our point is 1, 1 and our slope is 2. We've already learned how to use the point slope formula in our algebra classes. As we can see, the equation of the line contains the solution 1, 1, and we are already aware that our parabola contains the point 1, 1. So we have shown tangent line T is in fact a tangent on the curve y equals x squared. A few more comments about our numerical analysis side by side. Both of our numerical analyses show that as our point Q moves closer to P, the slope of our secant line gets infinitely close to 2. We can say that the slope of the tangent line T is the limit of the slopes of the secant lines. You may have been tempted to place our point Q exactly on point P to find the exact value of the slope. But if we had done that, we would have seen that the slope formula would fall apart. In other words, if we substituted x equals 1 into our slope formula, we would get the fraction 0 over 0, which can't be true. So the only thing we can do is study the behavior of our slope formula as it approaches x equals 1. From analyzing this behavior, we were able to gain valuable insight into what our slope would be. This process is called taking the limit. Taking the limit does not always have to be done in a numerical analysis. It can be done by visual inspection of a graph, in which mathematicians call by inspection or through inspection, and we can take the limit algebraically. You will learn how to find the limit in these ways in future lessons. So now we can answer our guiding question. So let's answer our guiding question. What is the definition of a tangent line to a curve? The answer. A tangent line to a curve is the limit of the slopes of the secant lines on that curve. The idea of a limit and taking the limit is the lifeblood of calculus. You will study the limit in many different ways as you go through this class in Calculus BC. It revolutionized how we interpret our natural world and is used in STEM and business fields. We found the idea of a limit by proving that a line touching a curve at one point is indeed a tangent line by finding the equation of that line to a curve. We saw that in order to find the slope of the tangent line, we had to draw a secant line and record a series of slopes in a numerical analysis moving to our fixed point, P at 1, 1, from a greater and lesser position. By analyzing the data, we were able to determine the slope and then use the point slope formula to derive the equation itself. We learned that when we analyze the behavior of a function as it moves toward a fixed point, we are finding the limit of that function. In our next class, we will study the notation of a limit, and we will practice finding a limit, still using a numerical analysis, and visual inspection. I look forward to seeing you. Thank you so much for joining me today. I hope you got a little insight into limits and their origins. My name is Madeline Bolden, and I hope to see you again soon.